Hello, I'm Max Truscott, host of the top-ranked Aviation News Talk podcast. It's a weekly show with news and tips for pilots and student pilots to keep you safe. I'm the author of several books, and I'm the 2008 National Flight Instructor of the Year. Today, we're talking with George Bye of Bye Aerospace, who's been on a quest for more than a dozen years to make electric aircraft a reality. George is working on certifying the eFlyer2 and eFlyer4 aircraft, and I asked him to talk with us about why pilots like you will want to fly electric airplanes, and when will it happen. Please hit subscribe so you don't miss next week's show, and now here's George Bye. Now let me tell you a little bit about George Bye. George grew up in a flying family where both parents were private pilots. He graduated from college with a degree in engineering. He then served about 12 years in the Air Force, where he was a T-38 instructor pilot, a C-147B aircraft commander, and instructor pilot. And he served in Panama, in Desert Shield, and in Desert Storm. Later, he worked for Flight Safety Services for 5 years on several projects, including as project manager for the T-6 JPATS, or Joint Primary Aircraft Training System. And the T-6, by the way, is a turboprop trainer used by the armed services and made by Beechcraft. He then founded Aviation Technology Group in Colorado, which designed and developed the Javelin jet, a high-performance twin-engine jet that bears some resemblance to the T-38s that George flew in the Air Force. A prototype of the Javelin was flown, but it didn't make it to market. For the past 12 plus years, George has been running Bye Aerospace. They are probably best known to GA pilots for their eFlyer2 and eFlyer4 all-electric aircraft, which are currently in the FAA certification process. They originally designed a process for converting Cessna 172s to electric propulsion. Later, they concluded a clean sheet design of an electric aircraft would be more efficient. Along the way, Bye Aerospace has provided engineering and design resources for Boeing as they pursued and later won the Air Force's Advanced Jet Training TX conceptual design program. They also have been involved with a number of solar electric UAVs, including the Strato AirNet, Silent Falcon, the Mars Solessa intended for use on Mars, and the Navy's Starlight. They're also in a partnership on the Trifan 600 hybrid electric VTOL business aircraft. Well, George, you've been pretty busy since we last met. Welcome to the show. It's great to talk to you again.
It's my pleasure. Thank you so much.
I'm curious, tell us how this quest began. I mean, what gave you the spark to pursue electric aircraft?
Oh, many years ago, I had the opportunity and honor to tour the very early conceptual process over at Tesla. They had just started the conversion of a couple of the Roadsters, and it was a very kind of new process. They were kind of diving into all of the challenges. The motor was the size of a watermelon. The battery system, of course, was very new and relatively complex compared to kind of the more efficient designs today. But oh my goodness, the test ride that I enjoyed afterwards was incredible, kind of the ludicrous zone that we see today. So that convinced me to the possibility that if electric was part of the future of ground transportation, that EVs were all of what they could be from efficiency, the CO2 environmental benefits, and potentially the ops cost benefits, that we needed to take a serious look at how it might apply to general aviation. And so that started the journey. That was the spark.
Yes, and I remember my first visit to the Tesla factory here in California, quite inspiring to see what's going on. Now, you often talk about the eFlyer 2 as being a purpose-built design. Now, as an engineer, that's one of my favorite kinds of designs, but explain for everybody just what a purpose-built design is. What does that mean?
Well, as you remember, we had the opportunity to use a Cessna 172 as a baseline kind of experiment for the very first look at what electric motors and batteries might be on a conventional general aviation airplane. And the firewall forward, the design, the mount, the electronics, how we might display that weight and balance, all of those things were all part of that early equation. And we learned a lot. But one of the things we could see almost immediately was, of course, a very great legacy design. That Cessna 172 is successful to this day because it's such a brilliant design 50, 60 years ago. However, purpose-built and the kind of the benefits of that particular configuration together with a Lycoming or a Continental is ideal as opposed to electric, which have much different characteristics. The size of an electric motor, in our case, about 17 inches in diameter, 4.5, 5 inches deep. So the large flat plate cross-sectional area of the nose can be dramatically different, and every opportunity to reduce drag and that very sleek, slim look that we have with the eFlyer is a tremendous reduction in the size, the slope of the curves around an electric motor as opposed to around a Lycoming or a Continental. And that means lower drag. The aero efficiency, the L over D of the airplane, literally you translate all of those benefits, not just the motor itself, but the air cooling required, the aerodynamics. We don't have fuel tanks in the wings. You can literally optimize those airfoils. So literally we have an L over D or aero efficiency twice that of the Cessna 172. An L over D of about 20 as opposed to 9.6. So for those of us who kind of have a little bit more of a engineering background or spend a little bit more time in the aero part of our pilot training, that's a big deal. Being able to glide twice as far or use half as much energy to stay aloft, oh my goodness, that is a game changer.
Well, and that's got to have a lot to do with endurance. I remember 10 years ago, you were talking about maybe an hour in the Cessna 172. What kind of things are you looking at in the eFlyer2? And is indeed that less drag a key to why you have better endurance?
Well, yes and no. The eFlyer 2 has a 3-hour flight endurance, by the way. The eFlyer 2 is specifically designed against the flight training mission. Specifically, we could design it with 4 or 5 hours of flight endurance like the eFlyer 4, but that's not its purpose. It doesn't exist, its role, it doesn't exist for long endurance, it exists for pilot training. One of the key things that's so important is that we're designing and developing aircraft against a problem to be solved. And of course, we want to reduce costs for all of general aviation, but the key in the immediate future, meaning 2, 3, 4 years out, is to address pilot training and getting new pilots into the profession, getting rusty pilots back in to enjoy the experience of flying, convenience of flying. The commercial, air taxi, air charter, all depend on pilots being available to operate those aircraft for business. All of that come right back to baseline is pilot training. And the number one objection to pilot training is cost. 85% drop out because of cost. Avgas is just expensive. So we're very proud of reducing noise. We're very proud to eliminate CO2. Oh my goodness, that's a big deal right now. But getting a 5-fold benefit to operating cost, 5 times lower operating cost, changes everything.
Yeah, certainly a huge advantage of electricity. We can pay much less per hour than we are when we're paying for avgas per hour. You mentioned that the nose of the airplane is smaller because you've got a much smaller motor in it, and that reduces the drag considerably because you're presenting a smaller surface to the wind. One of the things that surprised me is that also apparently makes your propeller more efficient. Explain why that is.
Yeah, so ultimately the width of the airplane is actually the same or wider than a conventional general aviation airplane. But what you're getting at there is what we call flat plate area, or the flat surface for the Lycoming or Continental that literally is presenting the air-cooled piston engine cylinders to the wind for air cooling. And an electric motor, you have a very sleek, gradual cowling and presentation to the wind. It's very gradual, a very pointed nose. Whereas a conventional Lycoming or Continental or Rotax really has to present, it needs to present those cylinders to be air cooled. So you have large inlets in a relatively large area, kind of 3 feet by 4 feet by 2.5 feet or something like that, roughly speaking, that needs to be air cooled. The difference is, of course, electric motors much, much smaller dimensionally. And so I can have a much more gradual and sleek presentation to the wind, reducing drag substantially. To your question about the propeller, that propeller on a conventional airplane, that first third span, is providing cooling air to the internal combustion engine. It's propelling, it's driving air like a fan through those openings and providing that cooling air for the cylinders. I don't have that requirement, and that first third span of the propeller is in the free open space as a tractor a prop providing thrust. Another 10, 12, 15% thrust for that first third span is available. And in other words, the overall propulsion efficiency, turning torque to thrust, is substantially improved because I have more propeller to present for the tractor function of the prop.
Yeah, I guess in essence, the prop sticks out further from the edges of the airplane than it does on the Cessna because it's a lot more narrow.
That's right. That's right.
Yeah. Yeah, that's really a great in a benefit of having the smaller nose. What about the wings? Obviously, conventional wing is carrying gas. What can you do differently that makes your plane more efficiently?
Well, as in most things in life, almost everything's a compromise, right? I mean, it seems like engineering is a forever task of compromise. Everything, as best as possible, you try to have dual use or triple use, but the bottom line is there's volume in wings, and the tradition is that we carry in that volume fuel. I don't have that constraint. I don't have fuel pumps. I don't have volume constraints for the carriage of fuel as a Cessna, Piper, Cirrus would otherwise require. So literally, my only design constraint is what is the best possible airfoil from root to tip. And I literally have 4 airfoils to optimize the shape of the airfoil, the incidence and twist, the airfoil itself as I progress from root to tip, including a winglet. And oh my goodness, for aerodynamicists, you're a nirvana. I mean, what fun to be able to optimize every aspect of that wing against the criteria for the flight envelope, rather than dual consideration to fuel carriage, fuel tank location, etc.
So let me see if I'm clear on that. So on each wing, the angle of incidence changes 4 different times as it goes out from the fuselage to the wingtip?
Well, as you go from root to tip, of course, it becomes twist, but the
Right.
incidence, of course, is the angle when you are mounted against the side of the fuselage there. But in any case, you're absolutely correct. We're constantly looking at airflow and airflow characteristics. As you know, in a flight trainer in particular, there's a great deal of focus with approach to stall, slow flight characteristics, landing characteristics, and of course, then you have side loads and gust loads and crosswind loads and things like that. So, and as you extend in our case, 2/3 span flaps, because we don't have drag. You think about that for a minute. And it's really true, of course, for the transport category aircraft that they go on to. These pilots are training for professional flying. And you use drag devices for flight path management. And that really is something for us that's not trivial. It's a part of a mindset in the behavior as a pilot learning to become a professional, that those drag devices, flaps are deployed not just for additional lift and slowing the stall speed down, but also as a flight path management tool for the final approach.
Well, I guess one other advantage in the wing is that you're probably not limited to the kind of structures you might have been limited to if you had a metal wing. I mean, are you able to create shapes with composites that you couldn't have in a metal airplane?
Indeed, it's not, as some would say, the black aluminum is sometimes kind of coined. Um, a lot of aircraft designers with a deep history in aluminum aircraft think, well, gee, I'm just going to use composite because that's kind of cool and modern. And effectively, they follow the same design criteria and process using or not using all of the benefits potential with composites. The 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 stiffening of the composite skin, the thicknesses, the varying thicknesses of composite skins. Of course, you still have the primary spar and secondary spar. There will be uh, uh, periodic other devices structurally that are more traditional or less traditional, but composites are highly adaptable and shapeable, and that allows, if well designed, well managed, it allows a very unique and special wing in this case or airplane to be created.
Well, I saw an announcement just in the last few days about parachutes for your aircraft. I was not aware that you had planned to have parachutes in the eFlyer 2 and 4. Is that something that goes back to the original design, something you've added along the way? And tell us what's different about this parachute solution from others on the market.
The the eFlyer family of aircraft have the opportunity to be the most modern, most high tech, if I might use an engineering term, the most cool airplanes. That's a high tech engineering term, let me tell you.
I like
Um,
that.
yeah. Oh my goodness. If we're going to start a new generation of general aviation, let's do it right, right? I mean, we've all been in this for decades and decades. Let's do this right. It's not a little incremental evolution. Let's do it right. And so, from a technology perspective, structural perspective, propulsion perspective, and yes, from a safety perspective, this should be the safest airplane of all time. And in our view, on occasion, it should be exceedingly rare, but every once in a while, you get yourself a pilot can find themselves, especially a student pilot, can find themselves in a box, and they don't have the airmanship, the judgment to avoid it in the first place, or they kind of get trapped by circumstances. I don't want to lose a pilot in that circumstance. Nobody does. And the ability to revert back to a full airplane safety parachute is a wonderful thing and worth every pound. We're delighted to work with a brand new parachute technology, a little bit lighter weight. It's a three chute rather than one large chute. So there's a little bit of redundancy and backup, but it's also a modern, lighter weight solution to get that safety recovery system available for every student pilot.
And do you have any idea how low you might be able to deploy it above the ground and still, come out of it?
Well, um, again, for from an operational manual perspective, we're going to be publishing, of course, the appropriate safety measures and protocols, the checklist for deployment and things like that. From a military background, of course, I flew in a jet training aircraft, the T-38, as you know, and we had ejection seats in that aircraft because of the nature of the business. But what's important, I think, to realize is that if there is literally no other alternative, but uh, an extreme event, it's always better to pull the parachute, even if you're not in the envelope. I'm not again, I'm not making a decision for other people. It's just a personal opinion, but generally speaking, revert to safety and parachutes if no other recourse is available.
And I'm wondering, a three parachute design, I'm certainly familiar with the single parachute in the Cirruses that I fly all the time. It occurred to me that it might be faster to fill three smaller parachutes than one large chute. Is that part of the advantage?
There is a faster deployment time, and the um, again, the potential is for lower altitude safety and lower speed safety. Again, there's a little bit of a trade-off between time and the amount of G-force and things like that. But the key thing here is a safe recovery, and the ability to critique the event after the fact with somebody who survived it rather than an event that is would be a tragedy.
Indeed. By the way, have you given thought to put any kind of data recorder in there so that you'll have some way to log what actually happened prior to an event?
There are some amazing technologies upcoming. And of course, we all talk about the interconnected world, and the typical conversations. What about AI and the airborne internet and things like that? Those kinds of things will enable that full time, real time availability of data, including a real-time link to your instructor pilot.
Hmm,
And imagine, student is out there and kind of struggling with a maneuver.
yeah.
If the potential is while he's solo or she's solo, your instructor is immediately accessible, or the instructor that's taking their turn. To be available for the student pilots up there flying solo. In any case, incredible technology is bringing incredible results, we think, to the future or the potential future of training.
We were talking about lower cost earlier. One thing that we didn't touch on was maintenance costs. Talk about maintenance costs as they relate to electrics as compared to conventional engines.
So, one moving part. That's it. One moving part. One moving part.
Sure.
946 moving parts in a Lycoming, one moving part in an electric motor. One moving part. Yes, you have torque, but it's smoothly applied. There's no, four-cylinder or six-cylinder and violent opposition, and all of the heat and shock and requirement for oil, et cetera, that's required with all of that. One moving part. Ball bearings, one moving part, and magnets. Smooth application of torque to provide thrust as opposed to an internal combustion engine. That translates to long life. That translates to relatively low cost. And the ability to maintain that motor, uh, periodically, probably we think longer inspection criteria. We'll have to prove that, of course, over time. But, I like to say my great grandmother's electric fan up in the attic from 1933, if I were to plug that in today, it would operate just fine. Just fine. Electric motors are robust, reliable, and the great reason for that is just an amazing electric motor that's taking electrons and turning them into torque and thrust.
Yeah, having lower parts count is going to help tremendously. Certainly, when we're calculating MTBF's mean time between failures, that's highly driven by the number of parts. So it sounds like your parts count is much low, and so arithmetically, it should be a more reliable airplane.
Exactly.
Good. So we've talked about all the benefits. There must be some trade-offs, as you and I discussed. We go to engineering school, and the first thing we learn is, hey, there's a trade-off for everything. You can't you can't get it all.
No free lunch, as they say, right?
Exactly. What are some of the trade-offs to an electric aircraft design? If someone were to buy an airplane, what are they giving up potentially?
So a lot of people like to talk about range anxiety. Now, of course, that's a little bit of a leftover from the EV. world, 5, 10, 15 years ago, most of the major automobile manufacturers were laughing off or being very dismissive of EVs. And of course, there was a little bit of that, of course, as we remember when the traditional aerospace OEMs were kind of dismissing carbon composite and the new innovations around that and the new OEMs coming out with that. It's our nature to be a little bit resistant to new technology. And quite frankly, it's not uncommon that there's hiccups along the way. From cell phones to computers, there's been successes and failures. But here we are today where that's commonplace. No different with electric aircraft. EVs right now are, in everybody's discussion from business to Wall Street, everybody's talking about EVs. And rather than what we were talking about a year or two ago, where it was, well, gee, I don't know if this industry is going to make it. Now it's the business to be in. And even somebody with an electric pickup concept has oh my goodness, $2 billion valuation, like overnight seemingly. So from a fixed wing general aviation perspective, we no longer have a technical hurdle for the convention of fixed wing general aviation flight, meaning Cessna 172, 182, Cirrus SR-20, SR-22, Piper Archer, etc., Tecnam and Diamond and all the rest. In that category and class of aircraft, I can create, and we are creating with eFlyer2, eFlyer4, and on, 3, 4, 5 hour, we can even go on from there, flight endurance, speed and range, which are equivalent. Again, a lot of people will kind of fixate on eFlyer2, and I would remind them it's specifically designed for a 3-hour flight time because its mission, and its only mission, is primary flight training. eFlyer4 has a 5-hour flight time. An amazing airplane, 175 knots at 12,500 feet. Absolutely every bit the equivalent of the 172, 182, SR-20, and others that would be considered comparable. And that's because, to your earlier question, the battery energy density, that is the amount of energy stored per unit weight, has now exceeded 250, 260, we're even at 270 watt hours per kilogram, which is sufficient in a general aviation purpose-built design, key purpose-built, to provide that equivalent general aviation performance.
And I can see as things start out with, flight training academies, they could set up chargers at a half a dozen airports, and that would work great. Let's project forward a couple of years beyond that. People may have a personal aircraft and they want to fly to, some particular destination. I read recently that Pipistrel and Green Motion have announced they're going to build a network of chargers. Is Bye Aerospace going to be involved in that, or do you have other kinds of charger plans for the airports here across the world?
Well, the ability for flight training to take place, as you know, is very much a kind of a hub and spoke where the aircraft come back to their takeoff point. The end of the mission, at the end of the day, all of the aircraft come home. And so, to your point, in terms of a charging network, you really solve 90% of your charging requirements with flight schools, the larger professional flight schools, when you take the charging system to the place of their deployment, their home airfield. Now, most flight schools have an auxiliary field or two, maybe 3 or 4 even, depending on the metro area where they operate. But the key thing is you have a relatively small, relatively concentrated requirement for flight training around these larger flight schools. and therefore a much easier charging requirement to be met. There's 5,000 airports or so across America, across the U.S. Relatively small number of airfields to solve the problem as you go beyond flight schools to, you know, air taxi or air cargo or even business aviation, and eventually even private aviation, where just for fun, you know, let's go fly somewhere. But to start with, our market is flight training, to be followed by air taxi and air cargo, where the business of aviation is tied to a relatively known, relatively small number of airports.
Got it. And if we project further beyond that, I don't know, 5, 10 years, whatever, maybe I have an eFlyer 4. What if I go to an airport without a charger? Will I have a power cord where I could at least charge slowly overnight, for example?
Absolutely. Yeah, you just roll out the plug-in. In fact, you could probably find more places to plug in your airplane than you can get avgas, and a much cheaper, by the way. So, yes, of course, um, you know, you fly out to your Nebraska farmland, and as many do today, you know. But the key thing is you don't have to have that 55-gallon drum of avgas there. You can literally plug it into the side of the barn.
Yeah, that does sound easier. Now, if somebody wanted to fly an electric airplane today, one of the few choices out there would be the Pipistrel Velis Electro. Now, they say recently that they've got the world's first type certificate for an electric aircraft. How does that certificate differ from the one that you're working on for the eFlyer 2?
It's dramatically different, and the use of words, the terms, the legal use of words is a little bit confusing for some in the market. And EASA, of course, a great organization. We're working with them too, but they use terms that are a little bit different than what we have here in the U.S. with the FAA. The Pipistrel aircraft, of course, is a light sport aircraft. And by definition, it has a weight limitation, 600 kilograms, about 1,300, a little bit more, 1,300 pounds, a little bit more than that. And it's meant, you know, with the various restrictions, to be kind of qualified by the company rather than by the regulator. There's not a review of the design as we have under Part 23. We've got 14 system-specific certification plans covering every detail of our design. Again, structure, aerodynamics, cabin safety, the avionics, instrumentation, high power system, in other words, the battery storage, the Part 33 certified motor. Every aspect of the airplane from a design perspective has been thoroughly reviewed, critiqued, from every aspect with the regulator. In our case, we're the world's first applicant and the only applicant for a fixed wing aircraft in the FAA as an electric aircraft. There is in the FAA today in the United States no electric light sport aircraft allowed. And one of the reasons, not to speak for the FAA, but one of the reasons is, of course, this level of detail and review from the design perspective, and then from a system-specific qualification perspective, meaning you go through and actually qualify each part individually, and then as a system, and then on the aircraft, all the way through a multi-year process. Ultimately, of course, conformed flight test aircraft, and the administrator finally signing off your type certificate and an airworthiness certificate that captures all of that IP, all of that process and that capability in a very great event, a very great asset too, I might add, from all of those years of work. So it is an entirely different. I think it's wonderful what Pipistrel has done. They should be congratulated, and I have. We often speak together at different events. But it's a light sport aircraft, and our aircraft is a 14 CFR Part 23 under Amendment 64, a type certified program, ultimately becoming the world's first type certified under Part 23 aircraft.
Great. Thanks for explaining that. I'm curious for folks that are early in your order queue, when might they expect to get their first eFlyer 2 out the door to them?
So we're in the 2-year time frame now. I wish I could say less. The coronavirus has been devastating to all of us. The FAA, our tier one suppliers, the setback is, of course, not just in aviation. It's not just in government. It's across the country and around the world. We've all felt the pain. And as best as we can assess, it will end up being about a half a year total impact, which puts us to about 2 years to first deliveries. We're going to do everything we can to try to work with our suppliers and the FAA to try to bring that back in. But the reality is, it has been a very challenging 6 or 7 months now, and we have the highest regard for the FAA, for our suppliers, but everybody's trying to do the best they can with the limitations.
Understood. So if you start shipping in roughly 2 years, I know you've got quite a large backlog. If somebody placed an order today, how many years roughly from now might they get shipped at the end of your backlog?
The answer is yes, they will. And of course, it depends because about two thirds, we have, as of the timing of this podcast, we have 360 paid purchase deposits. About two thirds of those are eFlyer 2s, one third are eFlyer 4s. So even though the eFlyer 4 will follow the 2 in the certification timeline by about a year, if someone were to put in an order for an eFlyer 4 today, they'd probably get it just about as fast as the eFlyer 2 customer would be, just because of the backlog and the way the schedule works out. So, give or take, uh, 3 to 4 years for an eFlyer 4 and about 3 to 4 years for eFlyer 2.
Well, I'm certainly convinced I would like to have an electric airplane. If someone's listening and they're interested in ordering one, is there a process? What do they do? How do they get in the queue?
Yeah, we are happy to answer questions from the market and provide information, help people go through the decision process. We have a paid purchase deposit agreement that potential customers are welcome to review. It's a small $5,000 deposit for the 2. The eFlyer 4 is a $10,000 deposit, and we'd be delighted to kind of explain how that works if somebody would like to place an order.
And why don't you go ahead and mention the list prices for both aircraft?
Well, it's 389 and 489, but I would caution against that. There's variability, of course, with every aircraft. You order a Piper Archer, and the first question the salesman will ask you is, "Well, wonderful, sign here, but what avionics package do you want? What interior do you want? What's your exterior preference?" And you kind of go through. A typically equipped aircraft may be 20 or 30, 40, even $50,000 more. And so you don't, ever really buy a baseline aircraft. You typically buy, a standard avionics package and whatever your preferred interior preferences might be. So probably a more typical price would be like 420 to 440 for the 2, and a little over 500, 540 or something like that for the eFlyer 4.
Got it. So, final question for you. This is kind of big picture, long term. Yet I've watched over time here the SR-22 become the best selling aircraft model. That occurred about 16 years ago, and they still sell more than any other individual model made by Cessna. I'm wondering, do you see a world where someday maybe the best selling aircraft model might come from Bye Aerospace?
Funny you should mention that because you and I both like, I come from a fast jet Air Force background, we might just have what's called the eFlyer X in mind.
Hmm.
And we love our friends up at Cirrus, but I would love to give them a real challenge with the eFlyer X. Maybe retract the gear, add a little bit of pressurization, and electric doesn't mind altitude at all. There's no turbocharging required for electric. We don't combust. We don't. There's no combustion process. So density altitude does not impact electric. So I intend to give a challenge to our friends there up at Cirrus one day.
George, this is all extremely exciting. When you get up in the morning, are you just really jazzed to go off and see what you can invent?
I am, and I'm honored. Truly, I am. But my goal is to have something of a legacy to pass along because I care about aviation. It's my industry. It's our industry, isn't it? I mean, for both of us. And if we do this well, we can pass along to the next generation of pilots something very, very special.
Wow. Hey, thanks so very much, George, for all that you do and for taking time to talk with us here today.
My pleasure.
Take care.